Hello everyone. So this is the second lecture of this week. Continuing the discussion of the last session, I will go over more about the model selection. Okay, in order to apply supervised model for the real practical problem, we have to consider several points. First, we have to determine the learning method, whether we have to use logical regression, LDA, SVM, or any other method. Once the method is determined, we have to find the optimal tuning parameters. In the polynomial regression, the highest order of the variable is the tuning parameters. Each method has different tuning parameters. Since usually many input variables are since many variables are available, another point is we want to use a subset of the input variables. Then the other consideration point is which subset we have to use. Okay? We have already discussed about the baseline assumptions and the characteristic of the various learning methods, as well as their tuning parameters. Based on this knowledge, you may be able to determine the method you want to use. However, we haven't really discussed about the variable selections. Variable selection is the general technique that can be applied to the most of the learning method. Here, in this session, we will focus on the variable selections. Traditionally, a supervised learning problem has many samples compared to the number of input variables, in the case that n is much larger than p. However, recently, with big data, the number of sample n increased a lot. However, at the same time, the kind of the available data or new information about samples increase much faster. That means increase of this p. So recently, there are many cases that n is similar with p, or even n is less than p. In this setting, most of the traditional learning method fails. To overcome this problem, we have to select most informative variables among many variables given. The first method for this purpose is the best subset selection. Among p predictors or variables, we want to select k best predictors. Here, the best often means the lowest MSE, definitely in the test set. The algorithm is simple. It starts with k is equal to 1. For each of x, we fit a model with only one variable. There will be in total p models. Among them, we select the best model and call it as M1. Okay? Then next step is when k equal to 2. Then we fit the model for the all combination of the two variables, like x1, combination of x1 and x2, and x1 and x3 up to x1 and xp. Similarly, x2 and x3 and blah blah blah. In total, p choose two models. By this way, we find the best model when we use 3 or 4 up to p variables. Finally, among M1, M2, and p models, find out the best model. Here, importantly, if we just use training MSE, this MP will be the best model at all the time because more flexible models have a lower training MSE. So we have to use other metric to reflect test MSE. If we want to evaluate the model truly. So instead of the training MSE, we can use like CP or BIC, or adjust R square, or we can use the cross validations. For a given learning method, the best subset selection provides definitely the best model. Okay? However, in total, 2 to the p models should be fitted. If this p is large, applying this best subset selection is practically infeasible. It's impossible. So, instead of this best subset selection model, best subset selection scheme, practically, these stepwise selection methods are more preferred. There are two stepwise selection methods, forward and backward. Forward stepwise selection first. This method starts from the null model, actually with nothing, which has no input variable. Then it adds the best variables one by one. Initially, forward stepwise selection fits p models using only one input variable for each of x1 and x2 and xp. Among these p models, it selects the best model. Then let's call it that is M1. This M1 is the best model when you use only one variable among p variables. Let's consider that best input variable is, let's say, x3 here. x3 is the best one single input variable that makes the best model. Okay? Then in the next turn, to find the best model with two input variables, we test model with x3 and x1 and with x3 and x2 in the pair of the model with the pair of the x3 and x1 and x3 and x2 and blah blah blah, x3 and xp. In total, p minus 1 models. So we add one more variable to the best model in the previous step. Okay? Among these p minus 1 models in this step, we find the best model and let's call it to M2. Okay? Then this is the best model with the two input variables. Let's consider the selected variable is x1. Then x3 and x1 is the best model. Then in the next round, when k is equal to 3, we add the one variable one by one to this x3 and x1. Then find out the best model with the three input variables. So in this way, we keep going up to the p input variables. So we make M1, M2, M3, and MP. So in total, there's a p best models. And among these p best models, we actually select truly best model. Definitely in this case, we need to use similarly CP, BIC, or cross validation. So in this forward stepwise selection case, in total, we need to fit only p times p plus 1 over 2 models, which is close to the p square models. Compared to the best subset selection that requires the 2 to the p model fitting, this computational requirement is much light. Definitely, it is feasible. The best subset selection guarantees the truly best subset of input variables because it actually evaluates all possible models. However, this forward stepwise selection does not guarantee. If we are lucky, the stepwise selection results the stepwise selection results in the truly best model, but in general, it doesn't. However, even though it doesn't always guarantee the best model, its semi-best model also works reasonably well in many practical cases. And the other is the backward stepwise selection. Backward stepwise selection is very similar to the forward stepwise selection, except the directions. It starts from a full model and remove the worst one by one. So for variable, the x1 and x2 and xp, it actually tests p minus 1 models that by removing one variable one by one. So first one is fit the model using only x1, x2, and xp minus 1. Then next is x1 and x2 and xp minus 2 and xp, just xp without xp minus 1. In this way, up to x2 to the xp. So among these p minus 1 model, we select the best model. So that model is the model that removing one worst one. So that's actually the model of MP minus 1. Okay? Definitely this MP is in the case that we include all models, all variables. So in this way, to find out the MP minus 2, we just remove the one worst variable in this way. So it is very similar. So similarly, in total, it needs to fit only p times p plus 1 over 2 models. Between this forward and backward stepwise selection, which one you want to use? If you guess the best model, uses only a few variables, then you may want to try forward stepwise selection first. But if you guess the best model use most of the variables, then you may want to try the backward stepwise selection first. It actually depends on your gut feeling. Okay. While this regular, okay, so the previous variable selection method, even though this variable selection method can be applied to any machine learning method, here for simplicity, let's focus on the linear model. In the linear model, there is the p input variables, and x, y is modeled by in this form. Here, the subset selection actually makes some selected betas to be 0. This is actually the subset selections do. So we can generalize this approach by reducing those betas, all of these betas, to 0, but with different rate. Okay, so some betas gonna reach the 0 first, but some betas gonna survive and selectively included in the model. This is the basic idea of this regularization method. The first regularization method is Ritchie regression. In Ritchie regression, we find beta 0 and beta 1 and beta p that minimize this whole of this target function. In the linear regression case, this first part is the RSS, the error term. And this, the RSS is the same with that of the ordinary linear regression. Then the second term is this one is called penalty term. Okay, or shrinkage term. So this Ritchie regression finds a beta that minimize both of RSS and this is the penalty terms. Without this penalty term, this beta can be any large value. But with this penalty term, small betas close to 0, those betas are more preferred. So this whole optimization problem try to find out such betas. Here, this lambda. This lambda is a tuning parameter that determines the weight between RSS and the penalty term. If lambda is 0, the penalty term itself is 0, so the Ritchie regression is equivalent to the ordinary linear regression. If this lambda is very large, RSS is almost ignored compared to this the penalty term. So minimizing penalty term will be dominant. So it results that all betas are very close to 0. This lambda is determined separately and open from the cross validation. We will see later this lambda determines actually the model flexibility. So this is the typical graph that shows the change of the 5 coefficients, 1, 2, 3, 4, 5 coefficients according to the lambda value. As we see, larger lambda make those coefficients close to 0. But these coefficients never get to 0. It actually gets close to 0, but never get to 0. So you will see why later. More importantly, different coefficients move toward 0 differently. This blue coefficient initially has a very large value, but it actually very quickly drop to the 0 point, then almost 0 at this point. Okay. However, this purple point, let's say this purple point, they are initially start with okay. So let's focus on this one. It actually initially start with the small coefficient and at the positive side, but it actually hit the 0, but it's negatively increased, and it actually survived the quite longer than others. This Ritchie regression doesn't shrink betas coefficients in the same way. If an input variable is not useful to minimize RSS, the Ritchie regression shrinks its coefficient first. If another variable is very good to reduce RSS, then its coefficient has a high chance to survive even with a large lambda. So Ritchie regression performs something similar with variable selection. Here is bias and variance trade-off. Ritchie regression regulates the variability of coefficients. It shrinks the model space. The model space is the set of models that this linear equation can express. So the Ritchie regression is less flexible than an ordinary linear regression. In other words, by introducing the penalty term, the Ritchie regression allows a bit larger RSS. It actually increases the bias. Instead, by reducing the model space, it decreases the model variance and increases the bias. So this is the bias-variance trade-off by flexibility. So this flexibility is actually controlled by this lambda. Another strong advantage of Ritchie regression is easy computation. This Ritchie regression has an analytic solution for any lambda, like this. It is like this. Please keep in mind that if lambda is 0, it actually makes this solution of the ordinary linear regression. Okay, so next is lasso. Lasso is very similar with the Ritchie regression, but its penalty term is given as the sum of the absolute value instead of the beta square. People often call Ritchie regression is L2 regularization. However, this lasso is L1 regularization. Because L2 means it has the second order, because Ritchie has the beta square, and L1 is the first order, so beta is just absolute value. But the concepts are similar. We want to prevent large coefficients, and we want to shrink them toward the zeros. As a result, we want to reduce the model space and make the model less flexible. The important point is between L1 and L2. First, finding coefficient minimizing this into the lasso target function, that is not that easy. it doesn't have an analytic solution. The solution should be found with a lot of computation. The efficient algorithm to find the coefficient of lasso was recently invented. In contrast, Ricci has an analytic solution and it's easy to calculate it and analyze it. It's why Ricci regression hasn't been used for a long time, while lasso recently has gained its attention. Lasso, or generally L1 penalty, is a very important technique because of its unique properties. Let's see this property. Let's see how coefficient changes as the change of the lambda. When lambda is low, the coefficient can be large. It can have any value it wants, right? It can have any value that actually minimizes this RSS. But as lambda increases, the coefficients are getting close to 0. Here is an important point. Different from Ricci regression, lasso penalty makes the coefficient exactly to be 0. So this coefficient is getting smaller and smaller, and at some point it exactly to be 0. Okay. Remind that Ricci regression makes the coefficients close to 0, but they never become 0. Since lasso can make some coefficient exactly to 0, it can automatically and truly select variables. For example, lambda at around 10 to the third, which is around this point, right? Only 2 variables has the non-zero coefficient among 5 variables. Okay, so it's a true variable selection. This is a strong advantage of the lasso. We will see later why lasso makes coefficient 0, but Ricci does not. The penalty term can be expressed as a constraint in the optimization problem. The optimization problem of Ricci is minimizing RSS plus lambda times some square of the betas. Okay, this is the target function. Minimizing this target function is equivalent to minimizing the same RSS in the constraint with a constraint that the square of the beta is less than equal to a certain value of S. In order to show two optimization problems are equivalent, we need some careful thought. But intuitively, you can see they share the same idea. The optimization with a constraint also prevents betas being too large, okay, because of by this constraint. By shrinking the coefficient, it reduces the model space, and the flexibility is controlled also, in this case, controlled by S. With small s, the model is more regularized, and it becomes less flexible. With the large S means, so that's why the large S means small lambda, and small s means large lambda. Okay. Anyway, Ricci regression is expressed in this way, with constraint the sum of the squares. Similarly, lasso is expressed by RSS, minimizing RSS, subject to this constraint that some of the absolute L1 values are less than S. Okay? And also, subset selection can be expressed in a similar way. Here, the constraint term is the sum of the indicator function. Indicator functions. Since an indicator function is 1 when the argument is inside the argument is true, this summation actually means that the number of the selected variables. So this concentrated means the number of the selected variables should be less than equal to S. Okay? So this optimization problem is finding coefficients with only S or less than S variables. These expressions show that Ricci and Lasso and subset selection, they all share a common idea of variable selection and reducing the model's flexibility. More importantly, the RSS part is expressed in this way because we are assuming the linear regressions case. Generally, the idea of the Ricci and Lasso and subset selection can be applied to any other machine learning method. In this optimization equation, by just replacing this RSS equation, we can apply these regularization ideas. For example, please Google deep learning with L1 regularization. You can find out a lot of papers. Okay, so finally, now let's see why Lasso makes some coefficient 0, but Ricci regression does not. Let's explain this point with the case of the linear regression. In the linear regression, RSS is given as the quadratic function of the betas, the second order functions, right? Then this beta head is the optimal point when there is no other constraint. With RS it gets larger, that corresponding betas actually make this contour in this form of the ellipse. Then about the constraints. Constraints, for example, in the Lasso case, this is in the Lasso case, it is given as the sum of the absolute values less than certain value of s. Then graphically, betas should be within this diamond area. Okay? So the whole optimization problem in the previous slide find out the contact point of this the ellipse with this the allowed regions by increasing the RSS by keep increasing this the RSS. Then contact point will be like this. Okay. You can easily see that regardless of the beta head's location, center point, and the shape of the ellipse, the contact point become the sharp point of this diamond on the axis. It means that the corresponding coefficient is 0. Okay? In contrast, in the Ricci regression case, the constraint region is given as a circle. Okay? Because it's the beta square. The contact points of this constraint circle and ellipse, usually it's not on the axis. It's somewhere around here, right? It's not on the axis. If we reduce the size of the constraint circle, then the contact point get close to 0, but never reach to 0. This is the reason. Okay, so here is the summary. Cross-validation is kind of the golden standard to evaluate a model with only the given data set. And the selection, but also the people traditionally have used the model selection criteria with a simple calculation, like the CP, BIC, or adjust R-square. Also, in order to select the variables, subset selection is a way to select predictive input variables in the whole data set. By sharing the same idea, regularization limits the value of the model parameters and reduces the model variance. Then it controls the flexibility. Okay, so here is a summary. You may want to refer a little bit more. And this is everything about the supervised learning in this course. And in the next, so you're gonna see some the numeric or programming example for this the model selection. Okay, so thank you very much. Thank you.